Alright, this is the second part in a Godot multiplayer series on the high-level versus low-level networking. And in this video, I'll take you through implementing a low-level networking approach. We will be creating the same scene setup as in the high-level example from a previous video, which is a small scene where you can connect multiple clients to the server and move around in 2D space. We will talk about TCP versus UDP, set up a network handler that takes care of starting the server and connecting the clients, creating packets, where I will show you how to encode and decode data types into a byte array, handle packet management to sort incoming packets and send them to the right place, create a 2D player whose position will be synced over the network, and create a player spawner that takes care of spawning the players. Once again, the project files will be available in the description, and without further ado, let's get into it. I'm currently experimenting with recording vocals, so you'll be hearing a bit of a mix in audio quality. My apologies in advance.
To transfer information over a network, we send something that's called a packet. A packet can be seen as an array of bytes where a bunch of information is encoded into these bytes. When we take a look at the Godot documentation, you'll see a section about TCP and UDP. A packet is sent using one of these so-called protocols. You don't have to fully understand the two to make multiplayer games, but it's nice to know some of the key differences. TCP ensures packets will always arrive reliably and in order, but latency is generally higher due to error correction. UDP only sends packets. No error correction makes it pretty quick, but packets may be lost along the way or received in the wrong order. In general, TCP can be thought of as reliable, ordered and slow, UDP as unreliable, unordered and fast.
Does that mean I use TCP for my turn-based RPG game and UDP for my fast-paced first-person shooter? Lucky for us, we don't have to choose, because most game engines offer a sort of midway implementation that uses the benefits of both protocols. Godot offers an implementation of ENet, which just happens to be a networking library built on top of UDP with the best features of UDP and TCP combined. The ENet documentation will also be linked in the description. Now let's start with building our network scene.
For this example, I've set up the same folder structure as for the high-level example, but for the low-level one. We already saw the ENetMultiplayerPeer in the high-level example, but now we are going to use the ENet library more directly to build the same scene setup for our low-level implementation. First, we'll make a new script called low-level network handler. Let's start with a few signals and variables we'll be using throughout the script. We need 3 server-side signals: when a client connects to or disconnects from our server, and when the server receives a packet. We also need 3 client-side signals: upon connecting and disconnecting, and when the client receives a packet. Then we'll add some server-side variables: available pair IDs, which is an array filled with available IDs, client pairs, which will be a dictionary with the pair ID as key and an ENet packet pair as value. Only one client-side variable, server pair, also of type ENet packet pair. And 2 general variables: connection, which is an ENet connection, and is server, a boolean to check if our running instance is the server. Let's begin with a start server and a start client function. This time, let's include the IP address and port as parameters. Both functions look pretty much the same. First, we create a new ENet connection. Then for the server, we use createHostBound using the IP address and port. For the client, we use createHost, passing in the value 1, as the first parameter of the function is the max amount of pairs, and the only pair the client should connect to is the server. Both functions return an error value. When there is an error, we print out the message that says server or client starting field along with an error string, set the connection to null, and return. If there was no error, we print server started in the server function and flip the isServer bool to true. And we print client started in the client function and connect to the host using the IP address and port. Next, we need to check every frame for incoming packets. In the process loop, first check if the server or client has started. We do this by checking if connection is null, then we return. Now we handle the packets in a separate function we call handle events. First, we'll create a new local variable called packetEvent of type array and assign it connection.service. When we hover over the service function, we'll see that we must call this function regularly to handle connections, disconnections, and to receive new packets. It will return an array with 4 elements, of which an event type and an ENet packet pair. We then retrieve the event type by grabbing the first element of the array and use it in a while loop where we check if the event type is not equal to event none. Inside our while loop, we'll assign the second element of the array to a new local variable called pair. Then we'll have to check what event we're dealing with in a switch case, or in GDScript also known as match. We have to check for 4 event types. On the event error event, we just push a warning and return. On the event connect event, when it's the server, we'll call peer connected and pass peer as a parameter. And if it's not the server, we'll call connected to server. Then we have to create a peer connected function with an ENetPacketPeer as a parameter. Here we'll assign the first available ID to a local variable peer ID and use it to add metadata to our peer. Adding metadata using setMeta is like adding a variable to an object without having to attach a script to it. We'll use it for the server to track what ID is attached to what peer. Below that, we'll add an entry to the client peer's dictionary with peer ID as key and peer as value. Then we'll just print a small success message and emit the on-peer connected signal. Let's also create the connected to server function, in which we'll only print a success message and emit the unconnected to server signal. Back in our match, on the event disconnect event, we'll do the same thing as with event connect, but for disconnecting. And again, we'll create the missing functions. In the peer disconnected function, we'll use getMeta to retrieve the peer ID. Push the ID back to the available peer IDs, remove the entry from the client peers, print the success message, and emit the on-peer disconnected signal. Then in the disconnected from server function, we'll print another success message, emit the on-disconnected from server signal, and set connection to null. Lastly, for our event disconnect event, below our disconnect from server function, we'll return because connection was set to null. Now for our last event, event receive, when it's the server, we'll emit the on-server packet signal along with the peer ID retrieved by getMeta and the actual packet retrieved by calling getPacket on our peer. When it's not the server, we'll emit the on-client packet signal, but now we'll only pass the packet. At the end of the while loop, but still inside its scope, we'll reassign packet event by calling servers again, and also reassign event type with the first value of the array. To finish the network handler, we'll add a disconnect client function that you can call when a user presses a disconnect button. First, check that when the server is calling the function, we'll return. And then we use serverPeer.peerDisconnect to request a disconnect. Now disconnecting happens automatically when you close the application, but I thought it would be nice to add a function for it regardless. Let's continue with the UI. We can just copy the high-level UI for this one and rename a bunch of stuff. And now we can replace the script with a new one called low-level client UI. And just like with the high-level network handler, we can make the low-level network handler an autoload so that we can access it directly from our UI script. And then start the server and client in the connected functions. Now the fun really begins, where we will be building our own packets. For our setup, we'll need 2 packet types. One to assign an ID to all the players and one to send a player position. But to create those packets, we'll first create a base class from which all packet types that we create will be derived. So in a new folder I'll call PacketInfo, we'll add a new script also called PacketInfo. In the new script, replace the extends node with PacketInfo as a class name so we can derive from this class later. Then we'll add an enum called packetType with the following 2 values inside, IDAssignment and PlayerPosition. And we only need 2 variables, packetType of our just created packetType and flag of type int. I'll explain the flag when it becomes relevant later. Now let's create an encode function that we can override in derived classes. This function will return a packed byte array. First we'll create a local variable called data of type packed byte array. We resize this array to 1 because our first byte will always be reserved for our packet type.
I will provide a more detailed explanation of resizing and encoding data types into a byte array when we create the player position packet. But for now, please follow along.
Then we encode our packet type into the data array at position 0 using the encode u8 function. At the end of our encode function, we return data. Then we also need a decode function that takes a packed byte array as a parameter. All we do is use the decode u8 function at position 0 to retrieve the packet type from our data array. We'll finish the script with a send and a broadcast function. To send something, we'll need an ENetPacketPeer to send to. On that target, we call the send function. The first parameter of the send function is the channel, which I won't go into detail about, but I'll leave a link in the description. For now, we'll just enter 0. The second parameter is the packet, so we can just call our encode function. And the third parameter is flag, where we can enter flag. We'll do nearly the same thing for the broadcast function, but it uses an ENetConnection instead of an ENetPacketPeer, and we use broadcast instead of send. Alright, now we can create a packet to assign IDs to our players. We'll need a new script in the PacketInfo folder and let's call it IDAssignment. At the top, replace the extends node with the class name IDAssignment and let it extend from PacketInfo. The data in this packet will be the following two variables: ID of type int and remote IDs of type array with int as value type. In a new static function called create, we'll provide the same names and types as our variables as parameters, and the function should return an IDAssignment. In the function, we'll set the following: packet type is set to IDAssignment, flag is set to flag reliable, ID is set to the ID parameter, and remote IDs is set to the remote IDs parameter. And then we return the constructed packet info. Now that the flag has become relevant, let me explain it. Remember the part about TCP versus UDP? Setting the flag as reliable makes the packet behave like a TCP packet, and ENet will internally try to make sure the packet arrives. That being said, when the flag is set to unsequenced, the packet behaves like a UDP packet, which is the flag we will be using when sending positions. Then we need another small static function that takes data, decodes that data, and directly creates a usable ID assignment for us. Now we should override the encode function. Instead of creating an empty data array, we use the parent class encoder to encode our packet info first. Then we resize the array to be at least size 2 plus the size of a remote IDs array. Then we encode ID and every remote ID in the remote IDs array. We should also override the decode function. Again, use the parent decode function first, and then we decode the data into the ID and remote IDs array. Next up is to create a packet to send player positions. For variables, we'll need an ID and a position in 2D. Then we'll make the static create function. Notice how I use PlayerPosition for packet type and unsequenced for flag this time. We can just copy the static create from data function from our IDAssignment class and replace the return type with PlayerPosition.
In the encode function, we first need to resize the array. Now let me explain how encoding works in a bit more detail. The most important thing to understand is that when we create an empty byte array, we need to resize the array to allocate enough space for our data. For that, we need to know the size per data type. If we look at the packed byte array documentation, we can see how many bytes each data type encodes into. In our base class, we already encoded the packet type into a single byte. Remember, 8 bits in 1 byte value from 0 to 255. So we can have 256 different types of packets. I don't want my game to have more than 256 players, so we should also encode the ID into a single byte. We can only encode a small section of data types, and vector2 is not one of them. However, a vector2 consists of two floats, x and y, and we can encode float values. Each float encodes into 4 bytes, so a vector2 takes up 8 bytes of space. So, to encode the packet type, ID, and position, we need 10 bytes of space. Now I'm using some random values to fill in the array, but this is what our position packet array can look like.
Our packet type is already encoded at offset position 0, so we encode ID at offset position 1. Since a float takes 4 bytes of space in our array, the difference in offset position should also be 4 bytes. Hence, we encode position X at offset 2 and position Y at offset 6. Lastly, we override the decode function again. Remember to call base class decoder first and use the correct decode data types and offset positions. Also notice that we can decode the data directly into a vector2. Now we need a system that takes care of reading the first byte of a packet, which is the packet type, and then generates the correct information. We'll separate the system into 2 autoloads, one for the server and one for the client, so other classes can connect to these autoloads and decide for themselves what to do with incoming packets. So let's create 2 new scripts, both extending from Node. One called server NetworkGlobals and the other client NetworkGlobals. And let's directly turn them into autoloads so we can get that out of the way. I call the classes NetworkGlobals because they store important information that should be accessible from everywhere. Let's start with the client side. We first need 2 variables, an ID of type int, which we'll set to -1 to check if it's set or unset later on, and remote IDs of type array with int as its value type to keep track of the IDs from remote clients. In the ready callback, let's connect the low-level network handler its on-client packet signal to a function with the same name. Then we'll also create that function below it. This function will take the received data, decode the first byte, and then match it with packet type. Right now, the only packet types that we have are IDAssignment and PlayerPosition. When a packet type is unhandled, we push an error. On the IDAssignment type, let's call a function manage_IDs, which takes an IDAssignment instance created from the data provided. And below, we should also create that function with the IDAssignment type as a parameter. First, we'll check if ID is assigned. If not, we'll assign it and emit a signal that the local ID has been assigned. Then for each incoming remote ID, we'll add it to our array and also emit a signal. In case ID was already assigned, the incoming ID is added to our array along with emitting the remote ID assignment signal. Last thing, we'll create a signal for the player position, which will be emitted when the incoming packet type is player position. Upon emitting, we can just pass in a player position instance created from the incoming data. Then we'll continue with the server side. The only variable we need here is pair IDs of type array with int as its value type. In the ready callback, we'll connect to 3 network handler signals, onPairConnected, onPairDisconnected, and onServerPacket, and create the functions accordingly. In the onPairConnected function, we'll add the connected pair ID to our pair IDs array. And now will actually be the first time we send data over the network. Let's create an IDAssignment and pass in the new pair ID and the pair IDs array. Then we'll broadcast our data, passing our ENetConnection, which we'll retrieve from the network handler. In the onPairDisconnected function, we'll just erase the pair ID from our array. To notify clients that are still connected to the server, we would need to make another packet type and broadcast it, something like an ID unassignment class, but I'll leave that up to you. Lastly, in our onServerPacket, we'll do the same thing as with the client, but only for the player position type, since the server will only be sending ID assignment types, not receiving them. So let's create a signal for the player position type. Notice that I'll also include the pair ID as a parameter. And down below, we'll emit the signal along with the pair ID and the player position instance created from data. It was quite a bumpy ride here, but now we should have all low-level networking systems in place. All that's left to do is create a PlayerSpawner, and a scene to run. For our player, we can copy the high-level player and its script from the previous video and just rename a bunch of stuff. We can remove the multiplayer synchronizer from the scene, as we'll handle the syncing ourselves. Then replace the script with our low-level copy. We need a variable to know which ID is the owner of the player. Let's create a property called isAuthority that returns a bool. IsAuthority is only true when it's not the server and when the owner ID is equal to the ID in our client NetworkGlobals. Now we can replace the authority check in the process loop with our own. Below the move and slide function, we'll create a player movement packet with our owner ID and global position and send it to the server using ServerPeer retrieved from the network handler. In the enter tree callback, let's address both our network globals and connect to the handle player position signals. In another callback, exit tree, we'll also disconnect those signals as good practice. And down below, we'll create the functions accordingly. On the server side, if the owner ID is not equal to the pair ID, we return. Lastly, we'll assign the retrieved position to our global position and broadcast the updated position. On the client side, when we receive a player position packet, we need to make sure it doesn't affect our player. We do this by returning when isAuthority is true. We also return when the owner ID doesn't match the retrieved ID to prevent updating the wrong player on our end. Below, assign the retrieved position to our global position again. Let's create a new normal node scene for our PlayerSpawner called low-level PlayerSpawner. Then let's attach a new script to it. Luckily, this will be a very small script. On top, drag in the low-end network player scene from the file system whilst holding Ctrl. We need a function to spawn the player, which requires an ID as a parameter. In there, we'll also instantiate a player and assign ID to the owner ID. We can also set the name of the player to the ID, but that's optional. Then, in a deferred call addChild along with the player. Lastly, in the ready callback, we'll connect our spawn player function to the following 3 signals. onPairConnected from the low-level network handler, which is only called by the server, handle local ID assignment from the client NetworkGlobals, and also to handle remote ID assignment. And with that, all the programming is done.
Finally, we need a 2D scene to run the game in. Just create a 2D scene that we'll call low-level example. And now we just drag in the low-level UI and the low-level player spawner, and that's already it.
Let's run the scene, shall we? Remember that you can add extra run instances by going to debug and then customize run instances. I'll set mine to 5 instances, one server, and 4 players. And just to showcase that everything works accordingly, I'll run one instance as a server and drag in all 4 other instances into the corner of my screen. And as you can see, every instance moves its own player while tracking the correct location of the other players.
And that's it for this tutorial on low-level multiplayer API. See you in the next one.